All right, so welcome back to part 3 of our little mini series on the rules for differentiation. Okay, so in the previous 2 lectures, we talked about kind of like the fundamental basic properties of taking the derivative on a function, provided that derivative exists, right? So what are the rules where, well, let's say like the power rule is probably one of the most important, right? So dx of x to the power n is equal to n times x power n minus 1. Like that one is just like we're going to use it so much that you're going to memorize it, right? What else? We know that the derivative is what I've been calling a linear map, right? So in the previous lecture, I said that we can apply the derivative of a sum, well, that's equal to the sum of the derivatives. But also, I kind of misspoke when I called it a linear map in that, like in reference to what I was saying about sums, because it also involves like the constants, like we can take constants out. Okay, so I'm going to write the constant property and this like sum property in one line to illustrate that point. So dx of, I don't know, c times f of x plus or minus k times g of x, that's equal to c times the derivative of f plus or minus k times the derivative of g. Okay, that's another important rule. We can distribute, in a sense, this derivative operator, and then we can take constants out. So c and k here are just any constants. Okay. So this is like part 1, and then in part 2, we learned about the product and quotient rules, right? So derivative with respect to x of f of x times g of x, well, that's equal to f of x times g prime of x plus g of x times f prime of x. Again, the prime is just indicating it's the derivative using a different notation, right? And again, this is just a sum. It doesn't matter the order in which you're multiplying f and g, just so long as you have function times the derivative of the other plus function times the derivative of the other. Okay? And then the messy one, the last one we covered, that was the quotient rule. And we have to be careful about the domain of G for the values of G over the domain in question, because we need to avoid this division by 0. So it's a hard one to remember. I even forget it sometimes. It's g of x times f prime of x minus f of x times g prime of x all over g of x squared. Okay. So that's kind of almost an exhaustive list. Of course, we talked about the derivative of cosine and sine, which using some of these rules, we can derive the derivative of tangent, cotangent, all the other trig functions as well. Now, before we get to the main topic of today's lecture, which is one, to me, a rule that I use all the time in my own work. Before we get to that, I just want to give an example of a problem that applies these rules in a way that I don't think that you as students would see immediately how to do if you haven't seen this, like, I don't want to call it a trick, but a trick before solving the problem. So this is using the rule rules that we know, not the new one that we'll learn today. And the problem says to find the equation of the tangent line to the graph of, what is the function I'm going to choose? F of x equals to 3 minus 1 over x all over x plus 5. And we want the equation of the tangent line at a point. We'll say at -1, comma 1. Okay. So I chose this example because there's several things that are going to happen. I'm going to rewrite this ratio using a technique that you should remember. I'm going to then calculate the derivative using the quotient rule. The derivative gives me the slope of the tangent line at a point. So to find the slope of this tangent line, to find the equation of the tangent line, I use that slope and the equation of a line at that point to then produce the final equation. So there's several parts to it, and it's illustrative of problems that you will encounter in the homework and most definitely on like your first exam. Okay. So let's walk through the solution. So the first technique that I'm going to apply is really common when you have x in the denominator somewhere, which that piece is in the numerator, right? Or if you have like something over x in the denominator, okay? And it's just, it's algebraically convenient to get rid of those types of things. So the only way to get rid of it is to, well, you can add 0 in a fancy way, or you can multiply by 1 in a fancy way, right? We don't want to change the function. We just want to make it look different. So if we want to do something to it, the only two algebraic things that we can do is multiply by 1 or add 0 in a clever way, right? So what I'm going to do is I'm going to multiply this function by a specific form of 1, the number 1. Okay. So here's the original form of the equation. This should be clearly equal to this. Right? Nothing changed. If x is not 0, I can multiply that thing by x over x. Nothing changed, right? That's a 1, right? Multiplying by 1 does not change the equation. It just makes it look different, possibly. It's like the reverse of factoring out and simplifying. Okay. So what happens when I distribute this x across the numerator and x across the denominator is that ratio, 1 over x, is going to go away. And I'll just say it out loud so that you think it's clear. So x times 3 is just 3x, right? And then x times 1 over x is what? It's just 1. So numerator now looks like that. And then in the denominator, I get x times x, which is just x squared. And then x times 5 is 5x. Okay, so it was just happens to be convenient algebraically to convert that into just get rid of that fraction by multiplying by that, right? So if you understand the idea, and like that was 1 over x squared, what would you multiply by to get rid of it? x squared over x squared, right? That would make that go like, that was a square right there, it'd go away, the fraction would reduce. Okay. So now that it looks like this, I'm going to apply the quotient rule to find the derivative of it. Okay. Now, admittedly, you didn't have to do that, but it will make your algebra easier if you do it. So this would be like part 1, part 2 is apply the quotient rule. So f prime of x is equal to the derivative with respect to x of that thing. Okay, it is a quotient. I really don't like using the prime notation with the dx notation. It bothers me, so I'm gonna write this as df dx, the derivative of f with respect to x. Staying consistent with my notation is just a thing that I like to do. Okay. So f of x is equal to this ratio. I apply the derivative operator on both sides. So df dx is equal to d dx of this thing, whatever that happens to be. That's that equation up there. All right, so I need to apply this rule. Okay. So as we did last time, I can identify my f and my g. Right, so I can say f of x is equal to 3x minus 1. And that's the original function is called f. I don't want to confuse you. I'll say h of x is equal to that, and g of x is equal to the denominator part. And the reason why I'm doing that is because I want to like clearly and as clearly as possible replicate this formula so I don't make any silly mistakes by putting a minus somewhere or the wrong derivative somewhere, right? So it's like h over g now. So wherever you see an f, think h. So in that formula, I see that I have to find the derivatives of those things. They're used, right? F prime is used and G prime is used. These are easy to take the derivative of by applying the power rule and the sum rule, right? So what all of this means is that, so h prime of x is equal to 3. Right? Take the derivative of h is just 3. And then g prime of x, it's 2x plus 5. By applying the power rule and the sum rule. So now that I have h, g, h prime, and g prime, I can just plug into that formula for the quotient rule. Okay, so it's going to be a mess. So I have g, so 2x plus 5 times, again, wherever you see an f over there, it's like an h over here. So g times f prime, or in this case, g times h prime, it's just, there's 3, minus.
But shouldn't we be putting instead of g prime?
Oh, I saw the wrong line. I read that.
Oh, okay.
I was trying to read that. Silly mistake. Thank you, by the way. Because that would have made a completely different answer. The ordering of this one, because it's subtraction, definitely matters. All right, so I'm going to give myself more room so I can think a little bit more clear. So here's g times f prime. So that's like, again, that h here. H prime, so minus, we have 3x minus 1, and then times the derivative of g. So all over g squared. really wish we had like sliding boards. I need more room. Even me, as a mathematician, I get jumbled up when I'm running out of room. So when you guys are writing these solutions, have a big sheet of paper. Right? That way you can stay like safe. All right, so now to the algebra part. This becomes 3x squared plus 15x minus, now I'm gonna use brackets because I don't want to like, notice there's a minus in there, a plus in there, there's a minus there. I'm leaving that to after I like simplify it a little bit. Okay. So 3x times 2x is what, 6x squared plus 15x minus 2x minus 5. So that's just that times that. And then in the denominator, I don't know if I'll need to really expand that out yet, so I'm not going to. Okay. I'm waiting until I see what happens in the numerator before I expand this denominator out. So I can just rewrite it. Okay, now I can send that minus in there. I can distribute that minus into this sum, and I'm good to go. Okay. Now, notice that just like you see these two terms right here, right? 15x and 2x. Like, how many of you in here would just like combine those like terms? I was not going to. And the reason why is that on the outside, I saw positive 15x minus 15x. They're going to go away. So it's just a little thing that you can think of, right? You don't have to combine them. If you see that there's the same quantity out there, don't combine them, just get rid of it. Just be careful with your signs, right? So I'm actually going to write out another line. Minus 6x squared here, minus that 15x plus 2x plus 5. And then all over this thing. Okay. Now, I'm hoping that I can squeeze it in right here. All right, so let's look. They're done. Like I said, they're going away. And then I have 3x squared minus 6x squared. I can combine those, right? And it becomes what? Right, negative 3x squared. So now I've taken care of these guys. And then I have plus 2x plus 5. All over that thing. Okay. So this is the derivative, and I can just use that to find the slope of the tangent line, right? That's the whole point behind doing this in a lot of cases. And I have to emphasize it again. Calculating the derivative, it tells you about the slope of these tangent lines to the curve of the function, right? And we are being asked right now to find the equation of one of the tangent line at that point. So now that we have the derivative of that function, which is this, I can barely see it, so if I make a mistake, let me know. It's 2x. Thank you. All over x squared all squared. Okay. Okay, so now we need to use this information here, right? This function, it's some curve in space, And at that point, there's a tangent line to that curve at that point, which means if we want to know the slope of that tangent line, we take that x and we plug it in there to that derivative, right? The derivative is telling us at any x that we put in there, as long as it exists, it'll tell us that slope. So we have to be careful though, because it's a big old mess. So choose that x there. All right, so -3 times -1 squared is 2 times -1 is 5 all over. I'm going to use brackets now. So -1 squared plus 5 times -1. And then all of that is being squared. I'm really happy that this example problem, that's a -1 and not like a 7 or something, because it becomes cumbersome to calculate. But luckily we have a nice -1. So -1 squared is +1, right? So this is all really equal to -3 minus 2 plus 5.
Equal to 0.
I don't have to do anything else, right? Not there, but like, it doesn't even matter like right here. Because if you have 0 in the denominator, 0 in the numerator, the whole thing becomes 0. Right? But I guess like, I don't know, maybe I should. 16?
Yeah.
But that's 0 on the top, it doesn't matter. That's interesting. This makes me wonder if I made a silly algebra mistake in all this mess over here, because 3x, 2x, 6 squared, 3x. Yeah, I think it's correct. And so, okay. The solution is very simple now. The slope of a line, the equation of a line is what? So y is equal to mx plus b, right? That's like one form of it. Another form is like y2, or I can say this. Y minus y1 is equal to m times x minus x1, right? And if you have a y and an x, you can find the equation of y. It's very simple though in this case because the slope is nothing, right? So it's just y is equal to 1, right? That n is 0. That's the thing we just found at that point, it's 0. So we're just left with y minus 1. So that means that y is equal to 1. That's the equation of a line. That is a line, right? It looks like this. Yeah. Okay. So interesting. Kind of curious what that looks like. We don't have the tools just yet to figure out what that looks like, but I'm curious as to the shape of it now that I know the tangent line is flat at that point. So -1, 1 is like, it's like here, right? So I know the curve either does that or does that at that point there. I don't know exactly, but we can figure that out maybe next week. Okay. All right, so lots of pieces, right? Lots of calculation, lots of tedious stuff. And sadly, this is a part of calculus, like taking calculus. This is not the essence of calculus, which is the cool stuff and thinking about rates of change and in surfaces and tangent lines. It's what's necessary to calculate things. It's like the tedious part, right? So especially for those of you that are in like science majors, like chemistry, biology, even especially mathematics, like this is a part of it. It's not the fun part, but it's a part of it. Okay. All right. So hopefully you got this in your notes now as an example, kind of working through a problem, finding a tangent line. Again, just to recap, to make sure, we rewrote the function, calculated the derivative, using this point, found the slope of the tangent line to that curve at that point, and then used this equation here to find the equation of the line with that slope going through that point. Now, those are the steps. Yes,
If we wouldn't have changed the equations, would we have gotten the same answer?
yes, because we didn't change anything.
We
We just multiplied by 1, and that never does anything bad. It just might have been a little bit more difficult to take the derivative of the top part. Think about it, like it's like you have to like put a -1, like it would be messy, right? Okay, so now on to the new. And this is called the chain rule. And it's one of the most important derivative rules, but especially for people that do like machine learning. This rule is just like, it's applied everywhere, right? Like just like if you've never heard about these things, there's these things called deep neural networks. And there's like a bunch of layers of like nodes connected to each other. You pass stuff in and you spit out some value. It's one of these, like, it's just a prediction, right? And then you can measure the prediction and then try to better it by using the derivatives, right? But to find the derivative of this like layered structure, we have to find the derivative of composite functions. Because like each layer you can think of as like composing a function with another, right? So what are composite functions? So maybe like recall just notation. So we have f little o of g of x. This is f evaluated at g of x. All right, so this is a composite function. And our goal is to understand how to take derivatives of such functions. And it's actually not, it's not difficult. It's just another rule that happens to be really useful to me. Okay, now the exact statement appears in the textbook, but for brevity and my short little stubby board here, I'm not going to write out the entire theorem. Okay, just assume that f and g are differentiable functions, so I don't have to write all of that business out. And also read the book. Okay, so here's the theorem. This is the chain rule. Okay. So, you know, I'm gonna have to write out something. It wouldn't make sense for me not to write out these conditions. So if y is equal f of u is a differentiable function of u. So the input variable here is u, not x. So it's a differentiable function of u. Okay. And u equals to g of x is a differentiable function of x then I can finally write what I wanted to write originally. dy dx is equal to the derivative, I'll just say it, I'll write it out first. dy du times du dx. So this is using Leibniz notation, which, as I mentioned before, is like kind of, I have a preference towards Leibniz notation. I'm not sure why, but I just do. But if we want to use the like prime notation, we could do something like this. So these are just equivalent ways of writing the chain rule. So what should I say here? Yeah, I'll use an X. Okay, so composite function, f composed of g. This is going to be the derivative of f of g times the derivative of g. Exactly. All right, so I feel like I really need to spend a moment to talk about the notation because it looks a little, I would imagine, confusing. All right, so I'm going to discuss notation here. So, all right, what do we know? We know that y is equal to f of u, okay? And u is itself a function of x, okay? U is a function of x, and it's a differentiable function of x, okay? So if I apply this derivative operator to both sides, okay, all I did was just apply the operator to both sides of that equation. That's it, right? So on the left-hand side, this is the derivative of y with respect to x, okay? So I just write dy dx. Okay, on the left-hand side. Now, what this chain rule is saying is that, so derivative of y with respect to x. Notice how often I say that. Even when I didn't introduce another variable prior, I always said with respect to something, right? Derivative with respect to some variable. So that's what this notation indicates to me. Maybe that's why I like it. When I look at this, I literally read derivative of y with respect to x. And when I read this, derivative of y with respect to u. And then here, derivative of u with respect to x. I like reading it that way. And then saying it out loud as I'm working because it kind of reminds me of what's happening, right? So, okay, here, so actually I'll write out something. I'm gonna mix up the notation now to talk about this one a little bit. So this is y, right? In there. That's y. Right? So we're going to take the derivative of that function. And we're assuming that that function is differentiable with respect to u. So that's where like this dy du comes from. It's a derivative of like the super function, the bigger function, which is the same type of, using the other notation, like this. Okay, it's a derivative of the outside function. That might help, actually, thinking of that. Times the derivative of the inside function. Okay. The inside function is u, right? Like that. It's the reason why, so these are equivalent. This is the same thing as that, it's just different ways of writing it. But again, when I look at this, it's hard for me to tell what the derivative is with respect to what. It's hard for me to just immediately say what variable it's taking. It seems confusing, but trust me, it's not so bad. In fact, let's just do like a quick example so that you're not afraid of it and you can start like thinking about it. So, and again, just to emphasize it, that's the chain. So let me pick like a very simple example. Like, I'll just make one up, I suppose. So we want to find the derivative of let's just say 3x squared plus 6x all cubed. Maybe this is a good example. I'm not sure yet. We'll find it. Okay. So this is a composite function. Okay. This is like the function like f of x equals to x cubed composed with this business on the inside. Okay. So maybe I'll just write that out. So x yeah. So I want to be as consistent with that to make it clear for you. So let me think about this for a second. So oh yeah, so y is equal to u and u is equal to 3x squared plus 6x. So you see that now this is consistent with this form, right? I replace u by that thing, it's precisely that. Does that make sense? Good? Okay. So if we want to find the derivative of y with respect to x, well, it's dy du times du dx. Dy du, right? The variable here is a u. So we can take the derivative of this with respect to u. So what's dy du? Right. 3u squared with power rule, right? 3 times u and then to the power 2. There's definitely a 2 in there. So that's dy du times du dx. And whatever that simplifies to, which it does, by the way, because right now I still have a u there, and typically you want this, you only want x's to appear. That's what you're trying to find, right? So this is equal to 3 times that all squared times that still. All right, so now that I've kind of hopefully emphasized the variable u, in this case, like treating u as a variable, we can make this drastically simpler. Right? This process of finding that derivative much simpler. I just had to spend some time kind of illustrating that we can take derivatives with things other than x, because I haven't done that yet. So I apologize if it seems a little bit convoluted seeming after I show you how to do this like normally, how I would do it. All right, so I'll just write it out. So one more time. All right. So what's the derivative of the outside function? Just treat this like a variable. It's 3 times this to the power 2, right? So it's 3 times the inside all to the power 2 times the derivative of the inside. Exactly. It's actually very simple to apply. Does that make sense? So let's like think about this, right? So let's do like another example. So find the derivative of y equals to sine of x squared. Again, we can think of this as like a composite function, right? Sine composed with x squared. Okay. So what's the derivative of the outside function? Right? Like maybe I should really like highlight that. It's sine composed with x squared. So the outside function is sine. Right? So, right, it's cosine, right? Cosine of whatever is in there, right? So the cosine of x squared, right? Times the derivative of the inside function, which is just what? X, done. Okay. And it's that simple. Okay. And yeah.
On the previous example, we don't have to distribute the 3 or the square.
You might have to, but that's the answer, right? Yeah.
Well, how about the u?
The u is replaced by this, right? Because that's what u is. Okay. You see that? So instead of writing u, I wrote it as the function of x that it is. Does that clear things up a little? Okay. So let's try another one. Let's do some more examples. The example that I made is so similar to the first example of the textbook. Cubed squared, it's a weird one. All right, same thing. For the sake of time, I'm not going to find the derivative. You know what we're doing. Y is equal to the cube root of x squared minus 1 all squared. Is there a square in there? I guess so. We want to find the derivative of that thing. How do we go about doing it? Well, I would immediately rewrite that radical to see what the power is, right? Well, it's just 1/3, just 1/3. Right? Whenever you have a radical, whatever's there is just 1 over that. Okay? So this is equal to, so I'm using brackets because I have parentheses inside. Okay. Now, oh, this is actually very convenient now because I see that 2, and I see the power up there. So what's the power of this actually going to be? What is the power rule for exponents? How would you remember if you forgot it? Like realistically, if you forgot, like, okay, so what I'm asking right now is like, what's going to happen like right there? What's the power going to be? That's what I'm asking, right? Which means that you need to know, like, okay, if you have that, like, what is that going to become, right? Like, suppose you forgot it, right? Suppose you forgot the rule. How would you remember it yourself? Like, I have a terrible memory, and I'm assuming maybe some of you as well.
Since they're parentheses, so we need to
But like why? Like how? Like if you forgot it, right? So let's just like think about this.
Multiplying equals adding and division equals.
Let's just put like a 2 there and see what happens, right? So what's this? Like this is just something to the power 4, right?
Mhm.
So just write it out 4 times. Right? It's the same thing. And then how many x's are in there? There's just 2, right? X to the power 2. How many x's do you have total? It's 8, right? 2, 4, 6,
Okay.
8, right? So this is like an example of applying this power rule. So now this isn't like for any, we did with a 2 and a 4, right? But maybe we can help, we can now understand a better way of like what this is. Again, I apologize if this is like you already like know for sure what that answer is. I'm just trying to make sure that you understand why it is. Right? So again, this is not calculus. This is what I would teach in like a college algebra course. So just like we did before, it's just a number multiplied by itself b times, right? So power a, makes the power a, dot, 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 makes the power a, right? And there's like b of these things. And there's b of them, right? And then how many x's are in there? Like in this parenthesis right here, how many x's are in there? A of them, right? So it's like this is x times x dot 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 times x, and there's a of them, right? But then the same thing here, right? X times x dot 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 times x, there's a of them, right? For each of these, dot dot dot, x times x times dot 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 times x, and then there's a there, right? So let's count them. How many total x's are multiplying each other, right? That's what we're trying to figure out. There's a plus a plus a dot dot dot. How many times are we adding a together? B times. So that means that this will be equal to x to the power a times b. That's how many that we have. If you forgot that rule, that's the power rule for exponents. Did that like you believe that this is the case now? Like we just literally counted them out. And that's why it is. Okay, so sorry about that little algebra tangent, but sometimes I find students in calculus that are like missing some things from algebra, and I don't like just jumping over it. So it's that power times that power. That's 2/3. Right. So now we can apply the chain rule and take the derivative. It's like u to the power 2/3 and u of x is equal to x squared minus 1. Okay, so dy dx, we apply the power rule. That is a rational number up there. It's a ratio. It's going to be 2 times 3. I mean, so 2/3 times the inside function to the power 2/3 minus 1. So that's the derivative of the outside part, right? Times the derivative of the inside part, which is just 2x. Right, so what's 2/3 minus 1? Yeah, negative 1/3. I don't like how all of you kind of looked up with blank faces when I asked that. Again, I'm like, maybe I'm feeling like especially like educational for the like simple math stuff today, but like, I really want to know like, how many of you like immediately knew the answer? 2/3 minus 1. So like maybe one person, right? But most of you probably not, right? So just think of it like this, like how far away is 2/3 from 1? And what could you add to it to get to 1? It's a third, right? It's 1/3 away from it, so it's gonna be -1/3. Okay. Y'all on board with that? Just a lot of times fractions, like dealing with them can be annoying for a lot of students because they never had like an actual, like someone teach them these things, right? Okay, so I think it's helpful to just look at how far away the ratio is from the other thing. Okay? Or like if you like pictures, like this is 1, you get rid of 1/3, you get rid of 2/3, you're left with 1/3. So, right, this is equal to 2/3 of x squared minus 1 to the power -1/3 times 2x. All right, so I see a negative exponent. You should probably fix that by taking the reciprocal. So altogether, this will be 4x over 3 times the cube root of x squared. Did I move too fast again?
From where did it get?
2x times 2. So that'd be 4x. All over 3 times this to the power of 1/3, which is equivalent to saying that. And this is the final answer.
I thought you could have made,
You can leave these radicals. You can leave them. It's just whenever you're going to take a derivative, like the radical is annoying. You want to write it as an exponent so you can use this like exponent rule for differentiation. So maybe I think like is the idea clear now? It's like, again, even when I'm writing out the solutions to derivatives of these types of problems, in my head I'm saying derivative of the outside times the derivative of the inside. I find myself actually saying this. Right? You just have to recognize what is what. Right? Like for example, like this one's like especially tricky. Like if you see something like that and you want to take the derivative of it, right? It looks just like the one we did earlier, right? Y is equal to sine x squared, right? But it's like a completely different thing, right? It's not x squared, it's cosine squared, right? So you would have to like kind of think for a second and say, oh, this is the same thing as saying cosine of x all squared. And then impress me, what's the derivative immediately? Not quite.
2 cosine x.
Say it fully.
2 cosine x.
You're missing something.
the times of derivative g.
What's the derivative of the outside?
2.
2 cosine x, right?
Mm.
Times what?
Oh, times
The derivative of the inside.
negative sign.
Mhm. And then then you're done. -2 cosine x times sine x. And you have to take the derivative of the inside as well, right? Okay. So I actually think, yeah, I think that'll be it for today. And I'm going to go ahead and assign you a section of homework on just applying the chain rule. Okay, so I'll stop the recording now.